Thanks for the introduction. Thanks for the organized invitation. Today I will talk about altermagnetic spin splitting torque and its inverse effect. And the first two topics is exactly related to the title. And the third part, I added this new results also from last Friday.
What's happening with Monday?
So, okay. For the application of antiferromagnetic spintronics, these are two typical devices. One is, for example, all electrical or antiferromagnetic junction. This is full antiferromagnetic junction. And also the other is we use this antiferromagnetic spin source to stabilize the traditional ferromagnetic junction. Both these kind of configurations need the spin splitting antiferromagnets with controllable spin current generation. This morning, Lieber and some other speakers introduced this famous altermagnet ruthenium oxide. So I do not repeat this anymore. And also, this material for the generation of spin current depends on the coaxial direction. For example, you can see here, for ruthenium oxide 100, when we drive the current in plane, then we get this spin current. This is transversal spin current, and the spin polarization is parallel to the near vector. This is very characteristic for the altermagnetic spin splitting effect. But differently, when the sample is ruthenium oxide 110 direction, for this sample, we only get this longitudinal spin polarized current. We cannot get this transversal spin current. So what is the advantage of this spin splitting effect? You can see here, for spin splitting torque shows this time reversal odd. This is quite similar to this spin transfer torque, which is sensitive to the ferromagnetic polarization. So this spin splitting torque is controllable. On the other hand, this spin splitting torque shows this transversal spin current is quite similar to the spin orbital torque with the large under the tunneling barrier. We do not have to drive the large current through the barrier, so the device is more robust. So spin splitting torque combines the time reversal odd and transversal. So we try to grow our samples in this cluster system. Of course, today I just use this sputtering system. Sometimes we combine MBE and sputtering, and we also do some in situ characterization in this system. We grow ruthenium oxide films by sputtering in the cluster system. One is ruthenium oxide 100, the other is 110 texture. Then we measure the spin torque FMR combining this ruthenium oxide and permalloy. This sample is permalloy with this ruthenium oxide 100 sample. It combines spin splitting torque and spin orbital torque. But for the control sample, ruthenium oxide 110 direction, there is only spin orbital torque, traditional spin orbital torque. You can see for the spin torque FMR signals, for this sample, you can see this symmetric signal is much larger than this control sample, indicating the larger the effective spin Hall angle here. We can see the ruthenium oxide 100, the effective spin Hall angle is much larger than the control sample. Also, we summarize the ruthenium oxide film thickness dependent sample. You can see this sample shows larger spin Hall angle for this 100 sample. Also, this sample shows very large spin diffusion length, almost 18 nanometers. So it combines this large spin Hall angle and the large spin diffusion length. Previously, for this heavy metal, always they are for example, for this platinum, tungsten with large spin Hall angle but very short spin diffusion length. But for copper, very small spin Hall angle, non spin diffusion length. So they are always contradict. But here, they combine together. Also, we try to demonstrate that this spin polarization is related to the new vector. Our method is to try to use this sample to get this field annealing. For example, when we annealing the sample along this y direction, from both the spin Hall effect and this spin splitting effect, the spin polarization is along y. So in this spin torque FMR signal, we can see only y damping torque. But when we annealing the sample, field annealing along x direction, that means for the traditional spin Hall effect, the spin polarization is along y-axis and the spin splitting effect along x direction. So the spin torque FMR signals have both. For this control sample, no matter what direction it is, so we can see here, both the samples only show this traditional direction. So there is no modulation of spin polarization in this control sample. Also, we demonstrate this effect in this ruthenium oxide 101 direction because this sample has this tilted spin polarization because for this ruthenium oxide, the z-axis is 001 direction. So for this sample, it shows the tilted spin polarization. Then you can see the XRD here. This is a substrate. This is a film. You can see the film quantity is good. And also, we measure this spin torque FMR. We can get this sigma z in this sample. Previously, for example, we demonstrated this sigma z. That means this is autoplane polarization in collinear manganese gold, for example. Also, manganese tin, manganese platinum. Here, we also demonstrated this sigma z in this ruthenium oxide system. Also, interestingly, we can demonstrate the field-free switching in this ruthenium oxide cobalt platinum multi-layers. When we drive the current along 010 direction, that means when the current is along this direction, the projection of the near vector is also along this direction. We can get this field-free switching. But differently, when we just arrive the current along this -101 direction, because there's no projection of the new vector, there's no field-free switching anymore. This is quite interesting. For the same sample, just drive the current in different direction. Then this experiment demonstrates the generation of sigma z in this sample, 101 ruthenium oxide. Then we go to this inverse spin splitting effect. Just now we demonstrated the generation of the spin current perpendicular to the charge current. Now we demonstrate the spin to charge convention in this system. That means when the spin current is along this direction, then we get the charge current perpendicular. We also use this tilted spin sample, this ruthenium oxide 101. We try to measure this sample by this spin seebeck effect. You know, for the spin seebeck effect, the spin polarization is along this x direction. The temperature gradient is along z direction. We can measure this voltage along y direction. But here, we can demonstrate that the voltage is not completely dependent on this configuration. It can depend on this. We can use this method to measure the sigma x and the sigma z in this sample. That means we grow this ruthenium oxide 101 sample. The new vector is along this direction. It parallel to 001, this easy axis. Then we try to measure this effect in different devices. The devices is like this, different devices. Then we fabricate devices along different directions. For example, when the phi is 0, that means the sample is along 010 direction. Then the phi is 90 degrees, that means it's along -101 direction. The sample is like this. This is the, we measure the spin seebeck voltage here. Then this is the heating layer separated by the silicon oxide. When we measure the angle-dependent devices, it satisfies the relation of sin 2 phi because the spins and the angle between the spins and the new vector is sin phi. And also the measurement voltage along different direction, the angle between the measurement voltage and the O10 axis is cosine phi. So we try to get this sin 2 phi relationship. Then we measure the one typical devices when the angle is 60 degrees. The original, the raw data is like this. It has some symmetric, this odd signal, and also this even signal. This odd signal is from the inverse spin splitting effect. And also this even signal is from anomalous length effect of permanently. Because when we scan the field, there is sometimes the permanently will go to y direction, producing the enormous length effect here. Then we summarize different heating current, the voltage, the specific voltage, and different heating current. We can see when the heating current, that means the temperature gradient is larger, then the signal is larger. Also, the different angle dependence, it satisfies this sin 2 phi direction. Because when the phi is zero, there is no new vector projection and the zero direction. For example, for the 90 degree, that means the device is along this -101 direction. There is no charge current along that direction. So both 0 degree and 90 degree show almost no voltage signal here. And also, we, go back. Also, we try to exclusion this anomalous Hall effect from the ferromagnetic metal. We measure, for example, we just use this gamma scan. That means we always make the magnetic field and sigma, the spin polarization along XOZ direction. There is no Y component, so there is no enormous length effect here. We can measure the spin splitting inverse effect. And also, we use this YIG because the YIG is not conductive. Also covered by this ruthenium oxide film, we can measure the signal both for the heating current, positive, negative, the signal almost the same. So this is also from inverse spin splitting effect. And also when we measure the voltage along this when the voltage is perpendicular to the field and linear direction, the signal is almost zero. A little bit of signal maybe from the defects of the films. And also when the measurement voltage is along field and linear direction, the signal is large. From these two experiments, we exclude the anomalous length effect from the permanently. And also, we try to grow the samples, ruthenium oxide and cobalt platinum by layers, because this is a PMA sample. So when we also show the same spin feedback effect, if this positive and negative current show the same spin feedback effect signal, the coercivity is very close to the enormous Hall effect of cobalt platinum, indicating the signal is really indicating from this cobalt platinum to the spin to charge convention in this system. And we also summarize different heating current dependent signal. We can see the signal increase with the larger thermal gradient. And also when the measurement voltage is along O10 direction, then we can measure very large signal. When the measurement voltage is along this -101 direction, there is no signal at all. Also, this effect can be measured by this terahertz emission. For example, for this terahertz emission for the 30 and 210 degree, here has two different signals. One is from this inverse spin splitting effect. The other is from the spin terahertz emission from ruthenium oxide itself. It's somehow opposite, but because spin splitting effect has this opposite signal, but ruthenium oxide itself has the same signal, so the signal is not completely the same. Then we try to extract the different signal between them, then summarize the terahertz signal as a different sample and different angles, also satisfy this sin 2 phi direction. You know, for this terahertz measurements is more clear. There is no enormous non-star effect here is more clear, and also for this perpendicular sample, it also shows this cosine phi direction. For the last several minutes, I try to report our quite new results on this altermagnetism electrical switching of new vector. And first, I show here that means this altermagnetism, in the altermagnetic material, the new vector is very important. That means electrical manipulation of new vector is quite critical in this community. The second slide, I show here why we want to switch 180 degrees. For example, in this kind of devices, for this switching of 180 degrees, it shows large TMR, and also it is possible for these two-terminal MRAM devices. So we want to get this deterministic 180 degree switching of the new vector. Previously, for example, Peter demonstrated this stacked field-like torque switching, and my group also demonstrated this damping-like torque switching. This kind of devices show this 90 degree switching or 120 degree switching. Also, the device needs a lot of terminal, and at least 4. But here is 8. So it's not good for the device integration. So 180 degree switching is quite important. And first, when we try to achieve 180 degree switching of new vector in altermagnet, first we want to how to read the 180 degree reversal of new vector. We do this calculation. It shows that when the new vector switching 180 degree, it brings about opposite Berry curvature and enormous Hall conductivity. We also demonstrate this here. You can see when the new vector is not switched, only switch the net moment in system, the enormous Hall conductivity does not change much. Only when the new vector is changed 180 degrees from positive to negative, it shows opposite enormous Hall conductivity. We also show this in this bulk in this circle for the north half and the south half. When we switch the new vector for 180 degrees, the enormous Hall conductivity is reversal. Then we show our samples in this manganese silicide. You can see we measure this enormous Hall conductivity here. This is the coercivity is somehow and this 6 or 7 kiloastud. And we also measure this magnetization by squid. You can see this is the some net moment almost 2 ml per cubic centimeter. You can see the coercivity is almost the same. This quite low coercivity here is from the defects. This from the DMI induced net moment can be also measured by these Mock measurements. We use this atomic spin simulation. We combine our results in the last slide. We can show that this DMI induced net moment which does not contribute to the enormous Hall conductivity, but helps magnetization of new vector. The new vector switching, the mechanism is like this. And first, we need to have this two minimum energy. It's very natural for this new vector. It's point positive to negative. This is natural two states. So two minimum energy is here. And first, when we drive the current along this new vector, then the spin polarization P is along this x direction. It drives some net moments along this direction by the damping like torque. Because of the exchange field between the new vector and the net moment, so there is the exchange field induced torque. It drives the rotation of the new vector. Then we apply this assistant field. For example, when the assistant field is along this y direction, it helps the switching from this positive to this direction for this rotation. And when it goes to this place, this magnetic field reduces or pins the switching anymore, so it can get this deterministic switching. When we drive the current oppositely, then the switching will be from this negative to positive again. So we can get this deterministic switching of the new vector from this physical picture. And also we demonstrate this effect here. We fabricate this whole devices here. We try to measure this. When this is the assistant field, this is the critical current, we can see the switching is here. Different from traditional spin-orbit torque in ferromagnets, the critical current is not so sensitive to the assistant field because this assistant field mainly works on the net moment. And also the spin orbit, this effective field from the current works on the new vector. So they work on different projects. And also, we can see the switching is fully for this assistant field is 0.2 kiloastot, 200 kiloastot. When the magnetic assistant field is very large, so there's no switching anymore because it can pin the switching. And also, the switching is very robust. We show here 500 cycles. The switching is good. Before the conclusion, I would like to thank my colleagues, the PhD students Baihua and Lei Han in my group, and also cooperation with Nanzhou and Hong Kong University of Science and Technology for some theoretical. Sorry, I write a wrong name here. Now I go to the conclusion. The first is we demonstrate altermagnetic spin splitting torque. We got this time reversal order transversal spin current. It shows crystal orientation dependent spin current and a new vector dependent spin polarization. We got sigma Z and field-free switching in this ruthenium oxide 101 sample. The second story is inverse effect. We can convert sigma X and sigma Z to charge current by the spin-Seebeck effect measurements. It shows crystal orientation dependent spin-Seebeck effect voltage. We can also use this method to modulate the terahertz emission. For the third part, we show this 180-degree electrical switching of new vector in manganese silicide. It's read out by enormous Hall effect and switching by spin orbit torque. Thank you very much.